Okay, so hello everybody, welcome to my talk on network retries. So it's great that this room is called testing and automation because it's kind of for both. So it's talk exactly useful for both of testing and automation. So few words about me. So I'm currently a software engineer at Red Hat, and I also a member of Weird Community Infra. That's our project, and we do continuous integration there and release automation, and we are responsible for all infrastructure. And as probably a lot of people, we use Python primary, and we have a lot of automation in Python. I also love DevOps, so I'm a strong advocate of DevOps way of doing stuff. And yeah, so if you don't know what is Ovirt, it's free virtualization management platform. There is a booth in building K, you can come. And about this talk, so it follows really real stories that I did. So we probably imagined we run a lot of automation in CI. Sometimes we have several thousand of job runs per day. And sometimes something fails due to a lot of reasons. In our automation, we use a lot of network services. We download packages from third-party repositories, from our repositories. And we use some REST APIs along the way during build and testing. So a lot of network services. And when you run 1,000 of jobs, sometimes you get failures. And usually they are sporadic, so the next run is okay. So you don't really look into them if there's just one failure, because you try to look for reproducible stuff. But it's still not good, because some of developers are frustrated, and we are frustrated because due to these random failures. And I just started this work on how we can retry it automatically. So if we can rerun ourselves and it works, why not let computer do that for you? And I needed a way to somehow test it, because if I just ask people about retries, they say, retries, it's easy. Just try accept and some sleep and some counter, and that's it. Okay, yeah, and the funny stuff, if you test it on your laptop, it probably work. You can see that, okay, it does retry. So is it enough? That the questions that I have. And I was looking for ways to really test how is it effective. So it's not just works, but does it really solve the problems that we have? Does it really effectively retry that? And that's when I come to this Linux traffic control. There was a talk, actually, one before this, about that they're using the same Linux kernel traffic management to simulate poor networks. And this all should be reproducible. It was my primary goal to make it reproducible, so you can find all the code, and I used in my GitHub page. There is also a large version of presentation with more text, because otherwise it will be hard to present. So for this, I cut everything possible. So let's start with some reasoning if failures we get are okay. So when you come here by plane, you probably didn't meet overbooking, but sometimes when you have a ticket for a plane, you may come to boarding, and they say, oh, sorry, we don't have any space in the plane left. You say, oh, how can it be? I have a ticket. But that's a mathematical concept, call it statistical multiplexing. So they essentially sell more space in a plane than there are, just in hopes that some people will miss it, so maybe two, and so they can sell more. And this is statistical thing, so they try to just predict that on these planes, the typical people are late. But sometimes it fails, and you just denied boarding due to no space, and it's pretty valid. So actually, this statistical multiplexing stuff is used in networks too. For example, if you had like circuit switching, it's like a telephone, right? You call in somebody, you have a line, and it's all yours. But it's not the case in TCP networks. They use packet switching, and you see you really share the bandwidth with somebody else. And if for some reason he wants all the bandwidth, then you are not lucky, and you may get failures just due to this. And it's not really a problem, it's just built-in, it's a feature. And so the thing is that really packet switching and networking system are just made to fail sometimes if demand is too strong. And it's not real failures. You can't blame network team for that if it's not happen often. It's just a feature. And The thing is that it's just mathematically, if you try something a lot of times and there is very rare chance of it failing, but if you try it a lot more times, then you will see it. It's just normal. So I must warn that you see the spherical code here, and since we do the simulations, we have to use spherical code. It's from a joke of physicists learning a cow by assuming the cow is a sphere. So we made some assumptions in this talk, and here, for example, I assume the importance, but it's not that important. So if it's this chain, and if you have automation, you probably have a lot of dependent parts, and each of them depends on the previous job completed successfully. And even inside jobs, you may call one service then another, and you really need all of them, all of those calls be lucky. And as you see here, so if you really have a kind of chain of dependent events, and there is a probability of each of them failing f. And then you, for example, have 100 steps, and probability f is small, so here's 0, 0, 0, 1. It's very small probabilities, but if you try it more times, then the final success of everything is, and if even, for example, this is your job, and you have like 100 jobs, then you will see here, like if you do 10,000 runs of this job that consists of 100 parts, it's very probable that it will fail at least once. So that's basically, given this overbooking, you will certainly see some failures if you have a lot of runs. It's just a fact. And that's what we consistently see in our systems. It's not all of them, but sometimes one or few in the days, they do fail. And this is actually not a bug. It's as intended. So in order to try it on my laptop, I set up this test environment. It was running on this old laptop. It uses containers. So basically, what I did is that I created a container with Nginx, so it's just HTTP server, put a file there, and was trying my Python code and downloading it. Then I used this Linux kernel feature to simulate poor networks, and then I was trying different solutions, see how badly they fail, and was trying to make something reliable out of it. And it's good that you really can test it on laptop. You don't need infrastructure for that. So this is basically how I did it. I just created a JSON file, just random 7 kilobytes file, and then just created Nginx from it. So then essentially our JSON file will be on this URL on the local box, and then we can try our Python code and just download it. So, but the tricky challenge here is that sometimes you configure this network simulator and the network is that bad enough that it just basically doesn't work. And you somehow need to know if the network was working or if it's your code not working, the network was okay. So, and there is a protocol called UDP, if somebody knows. It just basically doesn't have any checks if it arrived or not. It just throws packets continuously. And in order to check that network is working, I used this UDP, just netcat. It basically, like cat, it just throws dev random over the network. And then if you see UDP packets arriving, then you will see that the network is working. And if your request didn't finish, then it's kind of your code fault, not the network. But if UDP is not coming, I think network is that bad that probably nothing can be done. If somebody knows what to do, I will be happy to listen. And I also collected network traffic on this simulated setup. I use dump cap, it's Wireshark utility, you just dumps packets. And since I somehow needed to analyze it, I just export it into CSV files. And then once you have CSV files, you can use some graphing software. I use Octave, just because I used to it. But the thing is that here we basically record our TCP traffic because we are using HTTP, and HTTP is TCP. And we also record in our UDP traffic. And then we have these CSV files and we can load it into some system. So, okay, as a lot of people, so Request is nice library. It's very easy to work with, and we use Python requests in our infrastructure a lot, in our automation and our tests. And I started with this very basic, naive code. It's just get request using requests. It doesn't have any retries or anything. It just gets this URL. And here it will throw any exceptions if it happens, and we get JSON from it. So it converts from byte stream to JSON. That's what I did. So I ran it on my simulations using this sampler Pi. It's available on GitHub, but basically what it does, you specify the amount of thread pools that it uses, like 10 threads, and then how much times they need to repeat. And then it basically calls your function in the thread pool amount of time you specify. So this way I was simulating a lot of requests coming. And then I just did it also output CSV. It's nothing fancy, it's just a flag 0, it was okay, and 1, there was some error, and this is the time in seconds how much request took, just to understand it, how effective is it. Yeah, you can check its code, it's not that important. And then I run it, and using these CSV files, I managed to generate these nice graphs. So yeah, maybe it's not real, but you don't need the numbers. So just in gray, we have our UDP traffic. I scaled it down because UDP is very effective at just throwing packets. So if you don't scale it, will blow up all the screen. And this is our request, our TCP request that we made. So it was pretty fast. This is a histogram amount of requests occupying different times. So you see that it's here it's 0.02 seconds and like 20 requests, more than 20 requests. We finish it like in 0.02 seconds. So, and this is actually a pie chart. We had everything working. So all 100% of requests were completed successfully. And I believe this is how much of the network software got tested, right? So everything is working, it's very fast. Now we need somehow to make real networks that it's not really working good all the time, and just for you to give some heads up on how that's working. So when you use Python, which is a TCP layer model, it's not that important, but all our Python libraries we use request. It's actually, in fact, uses urllib3 inside. And then urllib3 calls socket, so socket is somehow on TCP level, but everything here on the data layer. And yeah, basically, if you don't know, it's a network model is just encapsulated, but important that everything that's down there for us, from our Python libraries, will look like either some data is coming, or there is just no data coming, or we get some kind of exception. So there are some mechanism here to make it somehow reliable, but for us it's all the same. And important stuff that I didn't really hack any libraries, I just tried to use what is available right now. That's important assumption for this talk. And so Linux Network Emulator is a part of Linux kernel. So in Linux kernel, it sits below the IP stack. There is a concept called client discipline. So it's what your ISP uses to limit amount of bandwidth that you have, for example. And in this discipline, there is a project called NetEm. It's network emulator. And it's used exactly for simulating poor networks. So it sits on the IP between the network device. Important stuff that it's applied only to outgoing packets. So if you want both ways, then you need to set it up on source and on destination too. But for our talk, we are not really working on IP stack, so it's fine. It has a lot of capabilities. It can simulate network delays. It can just simulate network loss and can corrupt packages and can create duplicate packages and can reorder packages so not arriving in proper order. And it also can rate limit it, so you can simulate like GPRS network just by limiting bandwidth. And network emulator does all that. For our purposes, it's enough to get loss because, as I said, for Python, it will be either data coming, no data coming, or just exception. So we're free to choose it. So we choose just to drop some packages. And this is, the probably hardest part. It's not that hard. So the problem is that nobody really knows how to simulate the real networks. It's just, they are really too complex to simulate them. So we really need some spherical cow, some model that will be good enough for us to simulate those networks. We don't pretend that it's very real, but if useful for us enough, then why not? And network emulator supports different models, so you explicitly configure it. So what I choose is a simple model called Gilbert-Elliott model. So it's just a state machine. It has good state and bad state. And then you specify probabilities of transitioning from one state to another. And then you specify also success and failure probabilities in each state. And then when you configure a network emulator, you will be just following this model with your probabilities. So also, if you assume, for example, in good state everything is working correct, and in bad state nothing is working, then basically you made a simplification and you'll need just two numbers, just with which probability we go from good to bad and from bad to good. That was simple enough. It's called simple Gilbert. It's the simplification of this model, and it's enough for our purposes. So, and this is why you need a bit understand that Markov state machine, because when you use Linux network emulator, you just have to specify here that you use Gilbert-Elliott model. There is no just magical switch make me poor network, because there is no poor network. They're all different. And so here you specify that you use this Gilbert-Elliott model, and then you basically specify the probability going to bad state and probability going to good state. And you just have to specify model parameters. There is no way to not do it. And it was actually very tricky to find some good numbers. You just play with it. And one important stuff, so on research papers, probability are usually given in decimals. And here it's in percents. So I first specified decimals. It was not clearly documented, and then it wasn't behaving like that, and that's because I had to specify percent. There are also show command you can see, and it will give you your parameters. So we specify just PNR, and since we assumed that in good state it's 100 success and in bad state 0, then it substituted those values themselves. And then if you already added this Q discipline, then if you want to change it, you need to use change command. So if you download my slides, there are references to the documentation of everything that is here, so you can just look up. But yeah, it's just basically we specified that with 50% probability we go from good state to bad, and 20% probability bad. So just so it stays in bad state a bit longer. So I ran it, and it actually was running over the night. So, and all the requests, this down graph is just the part here. It's first 60 seconds, so we had 45 requests when it's okay. Then there were no requests at all. It's just stuck. For all night, I just terminated it when I woke up. And as you see, UDP traffic was coming, so that's why I think the network was working. The funny stuff that we just forgot the timeout. It's not by default. By default, there is no timeout in that request. And as you see, without poor network, it's worked. But now we're just running over the night. It's just because we forgot this timeout. And this is from documentation. It says there is no explicit timeout by default. So, and again, so we can just get some timeout, but I just checked, so it's 95 percentile. So almost all requests finish it in 60 seconds. So why not just take this 60-second as a timeout? And here we go. So now this is how I should have written it before if I read the documentation. So I had to specify timeout here. And if we do that, then at least it finishes. I think finish it in a couple of minutes, and now we do have failures. So here is 26 requests failed, all other were okay. And this is the histogram. You see that most of the requests, it's like 40 requests took less than 20 seconds. And this is our timeout. It's 60 seconds, so those requests were aborted by timeout. You see it's like 20-something requests, and it's 60 seconds. So cool, we see the timeout is working, because that's exactly what I expect, 60. Okay, so now, does it at all make sense if we retry? Is it really doing any better for us? It's pretty trivial, right? So here, some requests, it's like 20-something requests, they were lucky, and they finished. So if we just retry, we try our luck more, and we have the same like probability of being successful. So the more we try, then we may get just more lucky next time. And that's why it just makes sense to retry. And just some note that in TCP there is a retransmission mechanism, right? So it's retransmitted packets, but it doesn't work when the TCP connection is not established. at all because there is no yet TCP connection. So like if there is DNS failure or you just can't connect, then you are not using it. And also there are some HTTP specific failures you can handle it from code, but obviously TCP won't retry it for them. So, but another stuff that we need to consider is it's safe. So if we just retry everything, can we mess up with something? And it turns out that in case of HTTP, there are requests that are safe because they just don't change anything, like get. We just get a page, so nothing changed. And there are also idempotent requests. It's a bit harder, but yeah, you can check it here. So it just changed something, but only once. So if you call this several times, it won't change it anymore. So here A was 1, then we called set A several times, and it's 2 and 2. So and another case is when nothing happened. So for example, our request didn't reach the remote server, and kind of nothing happened. And the libraries that we use request, it uses urllib3, and it has built-in support for HTTP retries. So it just knows all this, and it's available for you inside. So it's pretty much requests in urllib3 libraries that support retry in Python. So everything other does not. But as you find out, you can use urllib3 retry even in your code if you are not necessarily using urllib3. So here how you can retry with request library. So it accepts to HTTP adapter parameter calls max retries. So we set it 3, and it will retry 3 times. So okay, so it's probably good enough, right? So let's try, and 14 requests still failed if we just implemented 3 retries. And it was really looked some strange for me, because if you check on this histogram, you will see that so we enabled 3 retries and timeout is 60 seconds. So we would expect that at least 14 requests were retried here, so they should go 3 times 60, it's 180. But we don't really see anything here on this histogram. You see, it just they all failed somewhere here, but 3 attempts would get us here. So something didn't really work right. And I enabled the protocol debugging just to check what it does. This is how you can do it. You just enable Python logger for all the libraries you use in your stack. And I also disabled network. So with traffic control, you can just specify fails 100% both cases, and you will have no network. So it's kind of configurable network switch. It just did it so I will get instant failure. And that's what I got. So I really didn't see any retries there. It just doesn't retry. It was funny. And one important thing I noted is it's converted retries value 3, and it converted to some retry object. So it was something going on. So I checked it more, and it seems that in urllib3 there is nice concept of abstracting your retry functionality into classes. So and they have this retry class, and apparently it has more configurations than it converts to, because when it converts, it just sets this total value. But there are separate value for connect errors that happens when you connect, and for read errors that happens when you download. And what happened is just it didn't set it, so it wasn't really retry, for example, connection related errors, and that's why it didn't work. So as I said, so urllib3 it works for HTTP compliant services. If somebody violates HTTP standards, like they change something in GET request, then you're not lucky, you can't use it. But if it's compliant HTTP service, you can use it and it will be safe. So because there are non-compliant stuff, it's disabled by default, but for connect, the request just didn't get to remote server, so nothing happened. For it, if it's safe method and it retries safe method by default, something may break, but if it's your implementation, you know it. And yeah, it's also because retries on the cases when too many requests failed, like service not available. So the cases where the request didn't reach the remote server. So this is how you can use it. You create this object from relapse3, set your retries for connect, read errors, and then you just specify it instead of your number. And then instead of converted value, we will use the object. So let's see if it works. Yeah, so it's actually, when I tried it, it didn't work. But you now see that it does the retries. So it was one retry, several retries, then I skipped just for the space. And I was kidding this time because it really happened to me. I just forgot to enable the network. But that's the tricky part about simulation, because with those model and with others, it's really hard to simulate network that is just, for example, down for 5 minutes, and after 5 minutes it's up. But in real life, this can happen, and it's good time to speak about the backoff. So it's also relapse3 supports it. But what is backoff? It's just before trying again, we just wait for some time. It makes sense, right? It's like a sleep. And for example, imagine we don't have network here. The white is no network. Here we have some network. So if you have no sleep, obviously all our requests happen here, and there is no value, right? We can have some constant like sleep for 1 minute each time, right? It will be good because eventually it will catch it, but it's not that effective, because if, for example, network will start working here, then we will wait a long way. And the best thing to use is exponential backoff. It's just next attempt to wait is just exponentially longer and longer and longer. And relapse3 supports that. So this is from its code. That's how you can specify exponential backoff. It's from the library, but for you it will be just a value, so it's good. So you can specify backoff factor. It's basically, it will generate 0, 1, 2, and then it multiplies it by your factor. That's how you can get the longer delay. So okay, so we specified here just a parameter of this retry object. And then we try one more time. Funny stuff that it still didn't work. So it's absolutely the same as before. It's like it was 14 requests failed, and now we specify all these parameters, and we still get the same. And it's same as before. We don't really have anything retried 3 times with maximum timeout. So it's why we need to test, right? So it was. I also was pretty surprised. I checked the exceptions. And I found that there are 2 kinds of exceptions. One is somehow handled, it's just a warning, it says, okay, I'm retrying, and it's fine. But second is just a connection error. Wow, we should retry on connection errors, but we don't. How can that happen? And from here it appears they have a generator. So they essentially stream data out of relapse3. They have generators. And if failure happens already in this part of code, it's not handled by relapse3 library. So it's out of that library. That's why it fails, no matter what you said here. And if you are not hacking libraries, there is no way actually to override it. But retry is easy, right? Try except. So that's what we did. So we did try except. But it's important that we use actually these retry objects from relapse3 to retry it. So it's really better because they cared for this all HTTP stuff. You saw its complex formulas, idempotency, all the stuff. If we use it, then we get all of it for free. And what it does is just, it's inside the library. So when we do request, it checks it. If everything okay, you have a request. If not, they really throw max retry error exception. And then there is 2 ways. One is increment, and it will give you a new retry object, so it's actually immutable, so you can just use it here. And then there is a sleep. It's where the backoff happening. That's where it's sleeping. And this is actually pretty much how this library, like request or relapse3, uses this retry object. So we can do the same, but use this object from retry. And if you do it like this, we have one small problem, because if retry happens inside the library here, then it will retry one more time. If it happens here, then we retry it. And it appears that in maximum we now can retries, max retries, multiplied max retries. So this is because some retries handled by library, some are not. But it's not yet in request. But newer relapse3, I found that it actually outputs the retries object to use it along with response. So you can just take it from there and use in your loop and your try block. So then you won't have this problem. But unfortunately, with request, it's still not possible. But when they upgrade to new embedded library, it will be better. And that's actually another feature of Relay 3, that you can also specify retries just in request. You don't need all those HTTP adapters. It's not yet in request, but I think it probably will be possible to patch it. Okay, so now if we do all this, we have pretty good picture, right? It's just one request failed. So, and yeah, it's almost all requests. It's here it's 100, so it's maybe 15 seconds. A lot of requests finish in 50 seconds. So because we were not waiting for the full timeout, but maybe I'm an idealist, but I wanted all requests to be successful. Probably this is good enough, but yeah, if we just our target and make efficient retries, then we probably want to check what happened with that one request. And again, I went to my log, and this is how it failed. It's pretty rare case, but I see it on our production systems. Sometimes, for example, we were getting like half of RPM file. And actually, we were failing only when we tried to install that RPM file, because nothing before that detected that we failed to download it. And here a lot of people ask, oh, but in TCP we have these retransmissions. But as you see, it doesn't work really. So you might have broken file derived. And let's see what happens here. So we have error. So we try to call len on self-content inside this library, and it's just none. So there is no len for none. And somehow we just didn't detect it that we got no data back from HTTP. And I actually was flying here, I checked this, and it has, in HTTP you have the content length, right? So you specify how much is your content, but in Relay 3 and request, this check is disabled by default. It's just not checked, maybe because there are some wrong implementations, they report correct size. It's probably safe to disable. But if we disable checking of the length, we may get like this, because the connection just closed it because network was poor, and we thought that we basically got all the data. And then if we are not checking lengths, we will fail only when we try to use this data. That's actually what happens there. And there are also cases when you just don't specify lengths, there are streams, and we really have those systems, they just give us RPMs, but they don't specify the length. So just when it's done, then it's done. And then even if we check length, we can check it for that cases, and our automation will fail because we don't know if it's correct RPM. And I come up with, it's a bit ugly from code standpoint, because here we basically can check everything needed inside our code. If like we have try except block, then if needed we can even verify RPM itself, was it correctly delivered or not. And this is what I did here, because I didn't want it to change the libraries. But for this particular case, if you enable verification of length, it will work. If server, of course, specifies the length, it's not always the case. But if it doesn't, then we just can try to have JSON here. And if it fails, it will fail with type error. So it's demo only. Probably you shouldn't handle type error in your code, because it may be a valid programmer mistake. But if you just wrap it, then it may throw some invalid JSON. And then if you handle it here, it will basically retry it along with others. And if you use a retry object, then it build general implementation, but with your verification plugged in. And that's what I did for this case. And after that, everything was okay. Actually, I managed to get 100 requests passing with all this. And believe me, it was really poor network. I wouldn't want my network to be like that, because yeah, you see a lot of gaps, so it's just fluctuation. But it's magic retries, they can make you pretty successful even with that poor networks. And good stuff is that there are tools like built in Linux. This in all modern Linux distros has it, so you can test it on your laptop. So you don't need complex infrastructure for that. It's good. And so if you make some conclusions, so I would say then we can really emulate networks good enough for testing of network applications. It's just possible. It's not simulating real networks, but there are enough parameters so you can achieve your result. And clearly you saw that it was very successful and very fast in the beginning on local host network. So obviously testing network application with local host network is not enough. And I would also argue that even local network may not be enough sometimes if your application works with internet. It's certainly poorer than your local network. So even if you use local network, then you may still need to do something to test it better. And another thing, it's retry implementation is not that easy actually, because you see there's some knowledge that you need to have, and you need probably to read HTTP RFC, or you just use the existing solution, right? So you see this URLib3 implementation is general enough. You can just use this retry object in your code. It's not bound to URLib3 at all. You just pass it requests, types, and it outputs you if you retry or not. And another thing, you see that HTTP, they know, for example, this method you can retry, this method you cannot retry. And I know some people develop network protocols or network system, and think about it if you have it. So can you define some of your requests the way that your library can retry them without user even knowing? If you check like Amazon SDK, they actually have built-in retries inside because they know how the system working, and they just give users this for free. And that's what you should do for your systems if you develop this. And still provide some ability to customize it. You see how we use this URLib3 functionality to retry on completely non-valid JSON, so we can check JSON and then retry with it. So it's flexibility that some of your users might need, and it's really, as you see, it's all possible. So I did it on this laptop, so you also can do it. So if you have any questions, we have time for this now, but all this is available on GitHub. As I said, there is sample code that I was running and some Octa files to generate the graphs and the full version of presentation with more text. So you can use it to set up. And as I said, we use Docker containers, so it's really very easy to try on your laptop. And I encourage you to try it because I want it to be reproducible for you, so you can benefit from it. And there is my email and my Twitter, so feel free to ask there too. And so we now have time for questions. Yeah. It's actually have some. Yeah, I need to repeat. So it was a question: how fast does it change states? So actually, I don't know. It's as I understand, it's limited by actually your computer clock. So it has some clocking inside, and it's basically just each tick. It checks the probabilities and then transition or not. But I would say it's very fast even on this laptop. So if you specify it's like, yeah, network is working or not working multiple times, like microseconds. Yeah, so the question was if it works different on different computers, like with faster clocks. Yeah, I think that's the case, and that's why there's no just values, magic values that you can enable, and it says it's bad network. So that's why you have to somehow tune this model and try to play with probabilities. But yeah, changing it is just one command, so for yourself you can just try to adjust them and see what works for you. Because that's probably, I spend a lot of time with finding a good values for my code. Yeah, any more questions? Yeah.
I thought your URLib3 was very good, but it looks like you had to hack on top of it. With your experimentation, have you tested or found issues with other network library abstractions, or were you just focusing on Python?
Yeah, so this, so the question was that is it focusing on Python and did I check other stuff? No, actually I wasn't testing other libraries, so I was testing the Python because that's what we use, and yeah, the request library is very popular, so I would expect a lot of people use it, but it can be similar way to test it anything other because yeah, network emulator is in Linux. And yeah, I also probably will think about submitting some patches. So because there are certainly some stuff that can be improved. For example, if you can specify retry per request in request, it would be very useful for me at least. Okay, any more questions? Okay, I guess we are done.
Ik heb die andere ST 6 bereid. Dat is kijk natuurlijk blok of zo. Denk je.
Speak, turn that on, and I'll go to